Please make a brief introduction to the first keynote speakers, please.
So we are going to listen an interesting speech from Professor Hopgood, I mentioned, from the University of Portsmouth, United Kingdom. A very nice place, a seaside. His topic is about artificial intelligence for improved healthcare, and talking about the use of AI and in healthcare is a very interesting area, suggesting significant research values and practical implications. I mentioned before, Professor Hopgood is an internationally leading expert in artificial intelligence, intelligent systems, relevant research, teaching applications. He has also extensive experience of leadership, high level of leadership as a vice chancellor, provost chancellor, dean, across in different universities in Europe and in the UK. Okay, and again, I highlight his famous book, Intelligent Systems for Engineers and Scientists. Now, let's welcome Professor Adrian Hopgood. Hi, Adrian.
Hi, good afternoon, and thank you very much for that kind welcome and introduction. I'm now just going to share my screen to begin my presentation. Okay, I hope you can see my screen now. So I've chosen for my title today, Artificial Intelligence for Improved Healthcare. And these are the topics I'm going to cover. And I should say I have put my slides online on my website if anybody's interested in following up with the slides. They're at adrianhopgood.com/presentations. So what I'm going to cover today is I'll give a brief introduction to artificial intelligence, and then I'm going to cover 3 or possibly 4, depending on how time goes, areas of the use of artificial intelligence for improving the quality of healthcare. I'm going to look at predicting patient outcomes. I'm going to look at diagnosis and triage. I'm going to look at quality of health data and what can be done to improve it. And I'm going to look, if we've got time, I'll cover something on health monitoring as well. So that's what I'm going to be covering today. But first of all, we should start with the basics. So what is artificial intelligence? So if this was an in-person event, I might ask you to volunteer your answers. But since we're working virtually today, I will just say that a standard definition of artificial intelligence that's been around for around about 70 odd years since the idea were first floated initially by Alan Turing and then followed up by others, essentially mimicking human mental faculties with a machine. So human mental capabilities, if you like, with a machine. So that's quite a loose definition. First of all, it defines the challenge. It doesn't actually define how you're going to tackle it. And it raises a whole lot of other questions. So does the AI need to work like a human, or are you only interested in the end result, what it actually produces? And these days, in many specific domains, you expect the AI to actually exceed the human rather than just match it, particularly in terms of speed. Big question about whether AI needs to be able to explain itself. We talk about human intelligence, but is animal intelligence relevant? Many people find that a useful avenue of exploration, which leads on to the idea of all forms of biologically inspired computing being broadly seen as part of AI. The other thing to note is that what we understand by AI is constantly changing. So here's a quote from Rodney Brooks, one of the AI pioneers, who says, every time we figure out a piece of it, that is, say, AI, it stops being magical and we say, oh, that's just a computation. So our expectations are constantly moving on. So, for example, when I first started working in AI back in the 1980s, a big challenge was an artificially intelligent chess player. That was solved effectively in 1996 when Deep Blue beat the Grandmaster. So that was, the highest level of chess playing. We've got things like character recognition and speech recognition as well, which are effectively artificial intelligence that's in everyday use. And we kind of no longer think of it as AI anymore. So I said that the definition doesn't define the techniques. So let's have a look at the techniques that are available. Broadly speaking, AI can be broken down into knowledge-based intelligence and computational intelligence. So let's start with the blue circle there, computational intelligence. It's data-driven. And that's where most of the excitement and focus around AI is at the moment. I've put there neural networks and deep learning together, that you'd call those machine learning. And deep learning is effectively just a big neural network. And neural networks are good at spotting patterns in data. So that's what machine learning is really all about. It's about learning patterns in data and then using that learned information in new contexts for new problems. We've also got operational research, which is kind of mathematical approach to optimization, and then other optimization algorithms like genetic algorithms, etc. On the other side, the red circle, knowledge-based intelligence, has a long history, which takes a very different approach. Rather than looking at data, it's based on capturing what humans know, humans' expertise, typically in specialist domains. And a whole category of techniques there, like rules, case-based reasoning, model-based reasoning, frames, and so on. And then there are some techniques that fit between the two. They have elements of capturing human expertise, but also have a kind of data-driven model behind them, such as fuzzy logic and Bayesian updating. My personal interest in AI over many years has been to use the whole AI toolbox. And one particular technique I'm very fond of for delivering that is the so-called blackboard model, where it's rather than mimicking a single human, it's a bit like mimicking a team of humans gathered around a blackboard, or you might say a whiteboard, where they each contribute to the solution of a problem. And in this model, each of these experts might be a specialist AI technique using a different part of that artificial intelligence toolbox that I've shown you. And the diagram in the bottom right is a kind of schematic of how we've implemented it in computer software, where these specialist human agents are replaced by software agents, and they communicate via an area of shared memory called the blackboard. So that's a particular interest of mine, bringing together the whole range of AI techniques. Now, turning to the medical domain. This is a summary of the top 4 medical applications of AI according to Schmidt. He highlights diagnosis, treatment personalization, drugs development, and improved gene editing as the really hot topics. This afternoon, or this morning for me, I'm going to cover some examples under diagnosis and treatment personalization. I'm also going to talk about the quality of health data, which has implications for all 4 application areas. We're going to start now with a particular area which is under treatment personalization and specifically predicting patient outcomes. So I'm going to talk about colorectal cancer, more informally referred to as bowel cancer. It's the 3rd most common cancer in Europe. It is growing in prevalence across Asia. It is the 2nd most common cause of cancer death, and cases are rising as we grow older, populations grow older. Typically, we have a lifetime risk of 1 in 20 of suffering from bowel cancer. But the good news is that 90% of cases are cured by surgery. Surgery, though, is expensive. And it's not just the surgery itself, it's the hospital treatment. So patients would typically spend around a week in hospital, and that is a major part of the cost of their treatment. So it'd be really useful to have a good handle on the likely outcomes for patients following surgery. So we've used as a sort of guide for quality of care three aspects that we tried to predict: the length of stay in hospital, the likelihood of readmission to hospital, and the mortality, in other words, likelihood of death. So this is our data set. We've looked at 4,336 patient records, individual patients. And for each patient, we've looked at 47 variables. So first thing to note here actually is, although this is a useful data set, it's not enormous. So you can do quite a lot without having to use these vast data sets that are often referred to. So the approach we took was in two stages. First of all, to look at to do some data analytics, to look at which of these variables are important, and then built a predictor model. So starting with length of stay, this is the sort of analysis we were doing. So looking where a green bar here means a short length of stay of less than or equal to 6 days. A red bar means a long length of stay. So a green bar is good. And what you can see from here is that to have a short length of stay, it's good to have elective rather than emergency surgery. It's good to be younger. It's good to be fit. It's good to not have complications. It's good to have robotic surgery. Body mass index is not a strong indicator there, but it's also good to have a laparoscopic operation, so a small incision. So using this kind of data analytics approach, we were able to identify which were the most important variables. And then we built two types of predictor model, one using the whole data set and one using just the variables that we found most important. And let's have a look at some of the results, starting with length of stay. So this scatter diagram shows the predicted length of stay versus actual. And it's not actually that good from a first glance. It's quite a wide scatter. However, if you phrase the question differently and say, how good is it at predicting whether a patient stays in hospital for more or less than 6 days, which is a key sort of cutoff period, then it becomes much more accurate. As I say, we've looked at using the full set of input variables, 27 variables, and also just selected variables, just the 10 that have most impact. And it's interesting to look at the accuracy figure here. So accuracy now is whether the prediction is correct for predicting whether they'll stay for more or less than 6 days. So we've got around 83% accuracy using all variables, and almost the same if we use the subset of variables. And that's significant because it means that we could envisage building a more streamlined model. Now I'm going to turn to another parameter we try to predict, which is likelihood of readmission. Now this is more straightforward because it's a sort of yes/no. Green means not readmitted, so that's good. And again, you can see which are the important parameters here. So quickly glancing through them, having no previous surgery is good. Having a shorter operation is good. At least not having a long operation is good. Best to have elective rather than emergency surgery. Better not to have had a preoperative M stage. Best not to have additional procedures. Best not to have had a previous abdominal surgery. Again, best to be fit. And finally, better to have this surgery as a curative option, trying to cure the cancer rather than the palliative end of life care. Now, because this is a two-way classification, we can present the results differently. We can use the so-called ROC curve, receiver operating characteristic. So here we built a predictor model using bidirectional long short-term memory. It's a machine learning algorithm. The way this curve works is it doesn't only highlight accuracy, but also presents the the number of true positives and false positives. So basically, you want a high level of true positives and a low level of false positives. So you want the curve to go as close as possible to the top left-hand corner. So we're getting good results here with accuracy 87.5%, sensitivity 84%, and specificity over 90%. So really good predictor now of readmission. And let's move on to mortality. So we looked at mortality over different time horizons. Short-term, 90 days, so that's roughly 3 months, and also over 731 days, so 2 years. So a long time horizon over 2 years is good. So that's a green bar again. So again, so similar patterns again, looking at the data analytics stage, where elective surgery is better than emergency. Here, body mass index, well, actually, with all of them, body mass index is not a good indicator. Again, it's good to be curative, have curative rather than palliative surgery. It's good to not have complications. It's good to be fit. And it's good to not have a preoperative end stage. And now let's look at just the 91 days mortality, because there were various mortality horizons there. But if we just focus on one, we can make it a straightforward yes-no classification and present the receiver operating characteristic of the ROC curve. And we've got some really impressive statistics here with accuracy, sensitivity, and specificity all well over 90%. So this has been a really useful piece of work, and it really matters. So with this kind of powerful predictor, we can provide better patient risk stratification, providing patients into different groups according to the treatment they need, give them better individual patient care plans. We can better prioritize resources, and perhaps most importantly, the patients themselves can be better informed through consultation and make the best decisions for their own circumstances. So this work has been published this year in Discover Oncology, a major cancer journal. We have ambitions now to pool data with other centres, and also to consider photo and video evidence from the surgery. I'd like to also highlight the fact that we've had quite a lot of news coverage. So you can see the screenshot at the bottom there is a press release relating to this work. We have ambitions to separate out the colon and rectal cancer groups, which is one of the suggestions from one of the referees, and we've done a little bit of initial work on that actually, which is kind of interesting, showing some different characteristics for those two different groups, which I won't go into here. I'm now going to move on to a different medical application area, predicting intradialytic hypotension, IDH, in hemodialysis, or dialysis for short. So this is for people who need to use dialysis machines because their kidneys are not working well. And this a lot of people are affected. So in the UK alone, 3 million people, which is about 4.5% of the population, have some form of chronic kidney disease, and 30,000 of them are on hemodialysis. Now, IDH, intradialytic hypotension, is a sudden drop of blood pressure during dialysis, and it can lead to death, and it can certainly lead to a great deal of discomfort. So it's very similar methodology and a very similar approach. Basically, we're going to predict a patient outcome. In this case, we're going to aim to predict IDH, and by predicting it, we can hopefully avoid it. So a bigger data set here in terms of the number of dialysis sessions, although the number of patients involved is very similar to the number involved with the cancer study. But obviously, each patient has many dialysis sessions that we can use. And we've got these 33 variables. And it's a specific yes-no classification again. So again, we can use the ROC curve for presenting our predictor results. So on the left, we have a predictor of IDH using all our complete data set. And you can see we're getting accuracies, sensitivity, specificity, all in the high 70s 70%, above 75%. But there's a slight catch here, because some of the data in our dataset list of data variables I showed you are only available as you exit dialysis. They're not available before dialysis. So obviously those variables you cannot use as a predictor. As you enter dialysis, you don't have information about what the measurements are going to be after dialysis. So if you just restrict the predictor to using only the pre-dialysis data, the accuracy declines, but it's still useful at around 70%. A 70% indicator of possible IDH is still a very useful one. And in fact, the actual practical accuracy is probably somewhere between these two, because you are able to monitor some of these variables during dialysis. So you're not limited to just the pre-dialysis data, but equally you don't have the full post-dialysis picture. So that's two examples now I've covered about predicting patient outcomes, one in the colorectal cancer and another here for predicting IDH for dialysis patients. I'm going to turn now to a different domain, orthopedics. That's to say bones, and specifically bone fractures. And we've been working with some clinicians to better triage, that is to say, to sort the patients, to classify the patients on arrival according to the nature of their injuries as they arrive in the fracture clinic. We're looking specifically here at wrist fractures. And the idea is that if we can triage the patients, sort them into different groups, we can make much more efficient use of the surgeon's time, and we can make much more use of the available data, because hospitals around the world are now have an abundance of images, typically X-ray images in this case, but too little time to process them all. So let's have a look at the sort of things we're dealing with. For every wrist fracture, there's two views, sort of from above and from the side, giving you a pair of images. Lots of associate knowledge though. So for instance, children, young adults and older people have very different sorts of fractures. So for children, the bone growth plates are inherently a weak point, so they're likely to fracture there. Young adults have fairly strong bones, but find themselves involved in sort of high energy trauma, falling off motorbikes, skiing accidents, that sort of thing. Whereas older people tend to not have those sort of high energy impacts, but nonetheless suffer fractures more readily due to osteoporosis. So if you look at these images, there's it's actually quite hard to detect the fractures here. So I'm just going to highlight where these fractures have been highlighted by the clinicians. The clinicians have drawn on these yellow lines. So sometimes there's a clear sort of indicator on the original image of a dark line which hints at a fracture. In other cases, it's not so obvious. So it's a very specific expert task to classify these. So using standard machine learning alone will get us so far, but there's you really need to overlay some of the clinical understanding here. So they're looking for little ledges on the edge of the bones. They're looking for the information about the age of the patient and the type of injury they've suffered, as I've just mentioned. They're also looking at some of the natural angles between the bones. So if those angles are unusual, that's an indicator of a fracture, even if you cannot see a clear hairline shadow to indicate a fracture. So this is early work for us. So the stage we've reached so far is that we've achieved image segmentation. That's to say, for every image that's presented, we isolate just the useful X-ray part of that image. Really important to remove any kind of extraneous information which could mislead a machine learning algorithm. Lots of cases of machine learning algorithms that actually learn about the machine itself that's taken the picture, or the reference code that's in the corner, that sort of thing. So we've segmented automatically segmented the the X-ray image. We've used some publicly available data sets and achieved very high accuracy in terms of detecting fractures, well up into the high 90%, which is great. But those publicly available data are rather too easy, if you like. They're not the challenging data that you get in everyday life in the hospitals. So we now have a large hospital data set. The trouble is that they're not labeled, and you really need some labeled data to train a machine learning algorithm. So what we're using is the so-called Zooniverse approach, which enables many people to label the data, because it's an onerous task to ask one or two clinicians to label hundreds and thousands of X-ray images. So the way we're doing it is the Zooniverse approach, which enables many people to label them, but it's a closed community. We're just keeping it within the hospital. We're not asking people across the world. We're just asking relevant people working in the orthopedic area of the hospital. And we're aiming for a 7-way triage, a 7-way classification. In a way, most machine learning can be thought of as classifiers. You present your machine learning algorithm with many examples, and then when it's faced with a new example, it says, that's class A, class B, class C, etc. And that's what we're looking for here, a 7-way triage of patients, determining where they go next in the hospital. I'm now going to move on to a much more broad-based area, the area of health data, and we've called it healthy data. How do you improve health data quality? And there are many reasons why we might want to do this. So if we look at the first two potential benefits of having good quality health data, the first two relate to individual patients, so good outcomes for them and better clinical practice, better care for those patients. It can also lead to better health management. That's sort of looking at whole populations and how you manage them. So good examples of health management have occurred during the pandemic, where health professionals were making decisions about whole populations and how they should be treated and how they should be restricted in many ways. So good health data is absolutely important for health management. And then the last two categories, medical innovations and deeper knowledge of disease and treatment, are what really interests me. The fact that if you look at a country like the UK alone, a relatively small country with 65 million people, if we had 65 million accurate health records, that would be an amazing resource for medical innovation and better understanding of disease and treatment, because you'd have this 66 million records showing links between symptoms, diagnoses, treatments, medication, and patient outcomes. You wouldn't need vast clinical trials, because in a way, the human population is a clinical trial already in itself. So, so you could have vast improvements in medical understanding. The trouble is that medical records are unreliable. They have many errors in this country, in the UK, but around the world, it's a problem. They are unreliable. I should say that electronic health records are not the only health data source to underpin this kind of work. You also have clinical trials, wearable devices, genomics, health surveys, disease registries, etc. But we're going to focus on electronic health records. And as I say, they are around the world. There are problems with them being regarded as unreliable. So you've got some news headlines here from the UK, from Asia, from America. And where do those errors come from? Well, various ways. There's data entry errors, so the errors are inserted right at the point of entry. There's system errors, there's processing errors, there's contextual errors, and they all feed back into these into impacting these list of effects here: clinical care, biomedical studies, etc. So this work has actually been a PhD student of mine, Abinwa Zonzi, who's just completed his PhD actually successfulully, so that's good news. And he's built this taxonomy of error types. At the highest level, he's divided them down into incomplete data, incorrect data, and inconsistent data. So incomplete data will be sort of missing items. Incorrect data will be values that are wrong or in the wrong format. And inconsistent data may be data items that look okay in themselves, but are inconsistent with other data in the record. And let's look at some of the ways he's approached this. What he's done is to build a tool for spotting these errors, these anomalies, using a range of different techniques. So let's have a look. First of all, there's the so-called point anomalies. These are things that the cell is wrong in its own right. So if we look at the first highlighted one, that date of birth 14th of 07, 1690. Well, that's an unexpected, improbable date, because 1690 is an awfully long time ago. That's probably meant to have been 1960, a transposed date. We're using the European date format here, by the way, day, month, year. So there's a date that's wrong. Meanwhile, if we look at the gender, there are two expected values, types of value here. Well, there's the male and female, which can also be abbreviated to M and F. So there we've got an error. Somebody's entered masculine. That's not an expected word, so that's flagged as an error. There's a blank, so a missing value there. And then we've got female incorrectly spelt with two M's. So that's also a data error. So these are errors which are all point anomalies on the specific data cell. Then we got contextual anomalies, which across a single row. So you've got values there that might look okay in themselves, but they're wrong in the context of the neighboring values. So in the first example, we've got systolic blood pressure as the observation name, but it does not match the code that's alongside it. Further down, we've got some measurements which do not tally with the units of measurement that are alongside them. So those are contextual errors where each value cannot be correct with its neighboring value. And then we've got some collective anomalies, which are things which are wrong across values, across rows. So things here might be the case of sort of somebody who's male but also shown as pregnant, or there may be you may have a laboratory. You may have diagnosis before the laboratory investigation, or you may have the medication before the diagnosis. These things which are logically out of sequence. So the approach that's been taken here is to use three types of reference knowledge to build this error detector, using expert knowledge from the clinicians. So they define the heuristics, they provide the expertise. We've got explicit knowledge coming from clinical guidelines, vocabularies. This is published information, data dictionaries, well-published information where we can see exactly what the health data should look like. And then there's discovery. This is the machine learning aspect, statistical analysis and machine learning to look at data records and see things which are outliers, things which are inconsistent with normal expected patterns of medical data. And each of these approaches has its advantages and disadvantages. So if we look at the explicit knowledge from those data records, for instance, you can have very high confidence in that, and it's highly available. On the other hand, it's not easy to scale and manage, and it's not computable easily. On the other hand, if you look at discovery, the machine learning, that's great at being computable and scaling, but you may not have such high confidence in it, and it's not very good at explaining itself. So there's pros and cons for these three different approaches. The explicit data from the published guidelines, the expert data from the clinicians, and the machine learning. And Abin, what he's done is use a hybrid approach as I've already mentioned, actually using the expertise from the clinical experts, using the available clinical reference standards, using both data analytics and machine learning. And this is the sort of interface he's built. I'll just quickly through some slides here where he's built a system which enables you to interrogate the patient records, flag up errors, flag sort of things you're looking for, and build this sort of analysis where in this example we've got different types of errors are detected. If I look at the middle bar, date of birth, we've got there the red bar is invalid dates, the brown bar is missing values, you've got invalid formats, etc. Right. Just looking at the time, so I've got about another 5 minutes, so I think I'll move on to another topic here to round off. A quick look at something rather different and an unexpected overlap between the fields of cosmology and skin cancer. So this is an interesting case in point where the expertise that our cosmologists have at analysing images, large complicated images, has been applied in the medical domain. Specifically, they're looking at skin cancers. So this is an image of a patient who has a large number of moles, sometimes known as navi. Each mole is known as a navus, is its proper medical word, navi in the plural. So these navi in themselves are not harmless, but they can grow into skin cancer. And in fact, 60% of melanoma start from a pre-existing navus. So what would be really good would be to monitor these moles, these navi, through time to check for any changes. But that's not current clinical, or at least not common clinical practice. Normally, someone presents and shows their skin to the clinician who looks at it at that moment in time. They don't have that that monitoring of the changes through time. So this is where the cosmology comes in, because that's exactly what the cosmologists do. This is an image from the Dark Energy Survey, where they're looking at millions of galaxies, looking for these tiny changes. And to give you a sense, this is looking deep past our own galaxy. Just give you a sense of all these bright lights of galaxies. They're zooming right in and looking for tiny little changes. So you can see here a little oscillation of pixels, which are the kind of very subtle changes the cosmologists look for. Look at it. Here's another way of looking at it. Here's two images of the night sky side by side. Really hard to see the differences in time between them, but these are taken at different moments in time. If I now toggle those images, I don't know if you can see the slight flashing, which is the slight difference between the two images. You might just be able to see that, which is showing these minute changes in time. So in principle, this is effectively the same problem as the skin cancer problem. You're looking at these image features and looking for the tiny changes through time. So yeah, the stages are exactly the same. The left-hand side is the cosmology context. The right-hand side is the medical context. The first stage is to acquire the image and then to detect the sources. That's to isolate the areas of interest, if you like. So in the medical case, that's the navi, the moles. In the cosmology case, it's to identify potential supernovae. So in the cosmology case, they're really interested in supernovae class 1a, less interested in other ones. In the case of the skin cancer, we're really interested in the ones that are likely to evolve into skin cancer and looking for those subtle changes leading in that direction. So I'm towards the end of my time now, so I'm going to finish up with some conclusions. First of all, there is a range of AI techniques available. Lots of interest at the moment in neural networks for machine learning. As I said earlier, essentially classifiers learning patterns in large data sets, so that when you present with a new data item, it will recognize it. But that's not the only tool, and I think it's a really important lesson to not be totally focused just on machine learning. There's a long history of AI techniques for knowledge representation, using things like rules, cases, models to capture human expertise, which can augment what's coming out of machine learning. It can provide some validation, some explanation, some sense checking, and indeed some improved understanding. I've looked at some examples of AI in healthcare. So we looked at diagnosis and triage, which was the fractures, looked at treatment and care, looking at colorectal cancer, predicting patient outcomes, predicting the risk of IDH, intradialytic hypotension for dialysis patients. Also looked at health monitoring through skin cancer, monitoring those changes through time. Also looked at patient records, which I think have wide implications. I haven't touched on today, but another key area of AI that I'm interested in is independent living, supporting people to live in their own homes if they need help with their lives through, and AI can help flag when they need assistance. I've talked a little bit about health data quality. So good quality data is a problem for AI. It's a problem for AI that we don't have as good health records as we'd like. But I've also flagged that AI can provide a solution using various techniques to flag those errors and indeed propose corrections to those errors. I guess a more broad point is that, at least at the moment, with AI as it stands, AI is good at specific, narrow, repetitive tasks. So I don't think we're in any way likely to see clinicians being replaced in the near future. But what AI is really doing now is supporting them, helping them to do their jobs better. And it's been a great privilege for me to work with clinicians, mainly at the Portsmouth Hospitals University NHS Trust, who are all really enthusiastic about how AI can help them to do their work better. So here are some acknowledgements of the people I've worked with in these areas that I've flagged today. I've specifically picked out in the sort of the purpley color the clinicians. So the colorectal cancer clinician is Jim Kahn, dialysis care Nick Twangala, Robert Lewis, and for fracture triage we've got Philip Sauvé, Jeremy Rushbrook, and Ad Gandhi. And the other people there are my colleagues from the University of Portsmouth. Professor Lee was kind enough to highlight my book earlier. As he said, it's now available in its 4th edition, was released relatively recently. And if you visit my website at adrianhopgood.com, you'll find there's various software tools which you can download and play with that illustrate some of the points in the book. And that is the end of my presentation. I'd like to thank you for your attention, and I'll be very happy to take any questions. Thank you very much.
Thank you. Great. I like Professor Hopgood's presentation. Very interesting, research-oriented, and also practice-oriented, providing a significant research value, as I said before, and also significant practical implications and values to us, to the world, regarding using AI, artificial intelligence, intelligent systems, machine learning, for improving health care for everyone, saving lives, yeah, and improving our health. Very meaningful. Thank you very much. Any questions, ladies and gentlemen? Technically, not easy. I mean, a lot of technical applications, but with a very good introduction and provide a foundation for us as well. I learned artificial intelligence, and it's formally called knowledge-based systems. and intelligent system from Professor Adrian Hopgood's famous book, When Are We Young? Okay, very useful. But today's work, I think he has his collaborators, his PhD students made a focus on specific medical and health areas, and also very up to date regarding skin cancer. Currently with a high level of ultra X-ray to the earth, and also bone fracture. Very meaningful, very useful. Just again, ladies and gentlemen, any questions, please feel free to ask. Any questions? If not, I'll have a question. Adrian, ask
Okay.
me. You mentioned a very interesting technique about support vector regression. Yeah. Support vector regression.
Yeah.
Yeah. Do you think it's a very useful technique in your research, or any problem, weaknesses with it?
Well, what I didn't show today was that actually we tried a whole range of different machine learning techniques for this colorectal cancer work. I think from top of my memory, something like 10 different standard machine learning models to see which ones work best. And so you saw the support vector regression was our best predictor for length of stay, but actually for the other parameters that we were trying to predict, we did better with the bidirectional long short-term memory. So I think I'm not going to say that I prefer one technique from another, but they all seem, it sort of depends on your data set, which model is going to work best. They all have their sort of pros and cons. So I think it's really useful to understand how each of them works and to try different models with your data set, and it's a way of improving your outcomes if you can use the best model for the data that you're dealing with.
Yes, good advice, good points, good advice. Thank you. And another quick question is about you mentioned interesting points about data errors. Yes, inaccuracies and data errors everywhere, and also in business fields, in management errors, maybe more errors, more problems, more errors. Can you share your good practice and a good experience in research, your experience and a good practice in research regarding how to deal with random errors or inaccuracies? Can you share something with us?
Well, I think what you really need to do is to avoid the errors in the first place. So I think a proper analysis and proper gathering of data in the first place. So if I was starting a new project with a fresh with a view to doing some machine learning on some freshly gathered data, I'd think very carefully about what the data was, what format I needed it in, and make sure I had a nice clean data set right from the start. That would be the ideal. The trouble with medical data is that we have a legacy of data. So some members of the population, like myself, have quite a long health record, which goes back several decades. And of course, we can't start from scratch. We can't start from now. We've got to use the legacy data. So it's a different challenge. You're trying to make the best you can with flawed data. So so it's two different sort of aspects, really. I think if you're starting from scratch, design well, and there's lots of work being done now actually in the health domain to ensure proper, well thought out standards of health data records, so that from this point forwards we will have properly structured data, but it's not as straightforward as you might think, because you can design something that seems to capture every aspect that you might want to know. But there's the human aspect to consider as well, because the health professionals, the doctors, the nurses have to enter data. And if you make it too complicated, they will either not do it or will choose some sort of easy default option. So there are quite complex considerations there.
Yes.
So, I suppose another point that was learnt from the colorectal cancer data is that whilst it's generally true that the more data, the better, if you are having to make do with sort of compromised data sets, it is useful to spot that we got almost as good results with the reduced data set as with the full data set. So that's also interesting. So it means you can, for some of these models, just focus on the variables that matter. Yeah.
Thank you very much. Thank you very much indeed. Just again, any questions, ladies and gentlemen? We can take a couple of more questions, if any. Okay, maybe too technical, to be honest. Very interesting, very useful, very practical, very helpful, and exciting, interesting. Thank you again, Professor Hopgood. Thank you very much.
Well, thank you for your attention.
Thank you.
Bye-bye.
Bye. Bye. Hello, hello. Hello, Secretary. Hello. I can see.
Hi, Professor Lee.
It's my turn now.
Now it's time to have a